Okay, let's get into our second topic for the year, electricity and magnetism. And the first subtopic we're going to look at is electric fields. So if you haven't already, please make sure you just go and watch this video here, just on an introduction to charge and a bit of a review of what we would have looked at in year 11. So the first thing that we need to talk about when we talk about electric fields is something called Coulombs Law. And Coulombs Law tells us the magnitude or the size of the force between two objects because of their charge. And it's actually very similar in terms of, or very similar to Newton's law of universal gravitation. That tells us how much gravity two objects experience, or what gravitational force exists between two objects due to their mass. Coulomb's law tells us what force exists due to the charge on the objects. One thing maybe that it's important to note before we start is that the force, if you like, due to the electrostatic force is much greater generally than the gravitational force. This constant here is a bit like the constant in the gravitational relationship. That is 9.0 times 10 to the 9 is the value of that constant for the electrostatic force. Whereas in the case of gravity, I won't write it down because I don't want to confuse you, but I think it's like 6.67 times 10 to the minus 11. So 10 to the minus 11, really small number. 10 to the 9 is like a billion. 9 billion, this is a really large number. So generally, these forces for sort of comparable magnitudes of charge and mass are much larger. So, I digress a little. What does Coulomb's law tell us? Coulomb's law tells us the magnitude of these forces, so this is the magnitude of the force between two charged objects, is directly proportional to the product of the two charges, Q1 times Q2. We use Q as the symbol for charge, if you have forgotten that from last year, and inversely proportional to the square of the distance between them. And we use R to indicate the distance between them. So charge is Q, distance in this case is R, because often we're dealing with circular things and R indicates sort of the radius of a circle. So that relationship here tells us about the magnitude or the size of the force between two objects. Now, with gravity, the force was always attractive. There was no repulsive gravity. However, with the electrostatic force, you can either have an attractive or a repulsive force. And basically, what it tells us is that like charges will attract, so opposites will attract. So in this case here, two opposite charges will be attracted to each other, but like charges will repel. So, oops, that's not a pen, that's a rubber. Like charges will repel each other. So we just need to not only be conscious of the size of the force, but the direction. The third thing that we need to be able to do here is explain that the electric forces are consistent with Newton's third law, and any two stationary point charges experience mutual forces along the line joining them in line with Newton's third law. So the force that the positive attracts the negative with is equal and opposite to the force the negative attracts the positive. The force that this positive repels this one with is equal and opposite to the force that this one repels this one with, and so on. So that's why they are consistent with Newton's third law that says for every action force there is an equal and opposite reaction force. Let's keep going. So now we need to talk about the superposition of forces. And superposition is just a fancy word of saying, well, if more than two forces are exerted on an object the net force, the total force, is basically the vector sum of the two. And I think the easiest way to go through this is to look at a bit of a problem and go through that. So, and again, when we do these, we don't need to do anything too complicated mathematically. The vector addition will either involve a right-angled triangle, so we can use simple Pythag, an equilateral triangle, so all sides are the same length, so all angles are 60 degrees. You won't get anything too tricky there. So let's have a look at this question here. The diagram below shows and this is an old exam question, just if you're wondering where this has come from. The diagram below shows 3-point charges positioned at the corners of a right-angled triangle. The direction of north is also shown on the diagram. Charge QB has a magnitude of plus 2.56 times 10 to the minus 18 coulombs. QB is 0.80 meters from charge Q. The magnitude of charge Q is 8.0 times 10 to the minus 19 coulombs. Charge Q experiences a force towards the east of magnitude 2.9 times 10 to the minus 24 newtons due to QA. So it's not telling us the size of QA, but it's telling us the force. And first we need to calculate the magnitude of the force the charge experiences due to QB. So what's the force here? And then calculate the magnitude and direction of the total force. So basically we're going to work out the force due to B. We know the force due to A. We're going to add them together vectorially to work that out. So let's go and see how we do this. So for part A, we know that the force, the magnitude of the force, is given by Coulombs Law. QB is one of the charges, and the other charge here is Q. I just like doing the dot for the multiply. Divide by R squared. So if we substitute into that formula, we get 9 times 10 to the 9. That's off our formula sheet for that value. Times by 2.56 times 10 to the minus 18, times by 8 times 10 to the minus 19. I'm not really going to worry at this point about the sign because all that is going to affect is the direction, and I know that's positive. So the direction is going to basically be repulsion. That Q is basically going to be getting pushed down. Divide 0.080 meters, and that is squared. And quick check on the calculation. That is 2.88 times 10 to the minus 24 newtons. So that is part A done. I shall stick with that. So what then part B is calculate the magnitude and direction of the total force acting on Q. So we know that from the top, from that second part of the question, that the force here due to towards the east, yep, so that's the right direction. This here is the force due to charge A, and that's equal to 2.9 times 10 to the minus 24 newtons. Again, a little good check there. These numbers are similar size. This question wouldn't make sense if they were magnitudes different, so that sort of gives me an idea that answer to the previous part was a reasonable answer. And then we can see 2.9, 2.88, and in fact, I only had two significant figures there, so I should have actually rounded that off to 2.9. So that one there is 2.9 times 10 to the minus 24. Now, hopefully at this point you're going, well, if that length is equal to that length, even though they're not on my diagram, that the angle there will be 45 degrees. So the total force is given by that. We can work that out using Pythag. So Ft will equal the square root of 2.9 times 10 to the minus 24 squared plus, I'm just going to have to move that, 2.9 times 10 to the minus 24. Should add that all under the square root, but I think you get the idea. Squared, and that comes out to be 4.1 times 10 to the minus 24 newtons. But it's asked us not only for the magnitude or but also the direction. But we can probably pretty easily say that side there is equal to that side there, so that that angle in there is going to be 45 degrees. Therefore, the direction is going to be south 45, or sorry, let's back up a step, back up there, east 45 degrees south, or if we were using compass directions, we would say that direction there is southeast. If we couldn't recognise those with the two same, so it was 45, we could go through and use 10 or so. 10 would probably be the best relationship there. But generally, you're going to get ones that fall out pretty easily and pretty easy to work out. So that's the answer there for part B. So hopefully that demonstrates what we mean by superposition, basically adding together vectorially the two forces, and it also goes through an example of how we do that. So let's now talk about electric fields. And we've already talked about gravitational fields earlier in the year, and this I guess logic is very similar to what we used there. And we've got to take ourselves back a little bit in history, probably first back into history to where people didn't live in a world with things like radio communications and mobile phones and all that sort of thing. And this idea that, things that were not in contact with each other could basically, influence each other. And we also, I guess, need to take ourselves maybe back to our a bit earlier in our childhood when we talked about force fields and, like characters in computer games or kids' movies having these force fields that surround them and protect them. So, historically, when people started first looking at electric charges and things like Coulombs Law, they weren't happy with this explanation that two objects that were not in contact with each other could exert a force on each other. It went against what people's understanding of was. The idea of that understanding was, this is before people understood gravity and things like that, is that, you had to actually touch something to exert a force on it. And the idea of something exerting a force without being in contact, i.e. action at a distance, just didn't make sense. And the solution to that was to come up with basically this concept of force fields, which basically says that every object, due to its charge or its mass also in terms of gravity, has this force field that surrounds it. And when another charge comes along, the charge isn't interacting with the first charge that is some distance away that it's not in contact with, but it interacts with its force field that surrounds it. To me it seems a little bit redundant in this day and age, but that's why these concept of electric fields and also gravitational fields earlier was developed. So what we say is that electric charges establish an electric field, which we give the symbol E, in the surrounding space. The electric field at any point produces a force on an electric charge placed at that point. So this second electric charge interacts with the field of the first point. The electric field at a point is defined as the electric force per unit charge on a small positive test charge Q placed at that point, providing that all charges remain undisturbed. E equals F on Q. So that's basically just saying mathematically force per unit charge. Per is like divide. The direction of the electric force on a charge is parallel to the electric field if the charge is positive, i.e. the direction of the field is basically the force experienced by a positive charge, and anti-parallel, i.e. the opposite direction if the charge is negative. That'll become evident, I think, as we go on. So, we need to basically use this electric field definition here, E equals F on Q, and Coulombs Law. Coulombs Law, it's not here, but we talked about previously, and we need to use that to derive this formula. So what are we talking about here? Let's say we have two charges. We have one charge here. Let's call that Q. And then we have another charge here, which I'm just going to call QT. That's our test charge. Yeah, I think that's the best to use. That's what we use there. It doesn't really matter, the notation. So now don't think about these two forces interacting at a distance. We think about this charge here, Q, has this force field that surrounds it, and this charge QT is going to interact with that. Now, we know that by definition, the electric field strength will be equal to F on QT. So the force per unit charge, per unit test charge there. Now we can rearrange that formula and we get force is equal to E times QT. But we also know, and I might just do, sorry, I just lost my thing. I might just do a second column here. We also know that the, let's just put it both down here. We know that the force due to Coulombs law is equal to 1 on 4 pi epsilon naught, the constant Q, this charge, the first charge, times QT over R squared. So those two forces there should be equal. Therefore, we can say that E times QT is going to be equal to 1 on 4 pi epsilon naught Q times Q, the test charge, divided by R squared. And we can see that the QT and the QT there cancel out, and we get left with the electric field strength at that point where QT is equal to 1 on 4 pi epsilon naught Q on R squared. So I think that's a pretty simple derivation. If you're a little bit confused, you're probably missing how simple it is, so just have another quick look at it. So you need to be able to basically solve problems with this electric field formula and the electric field definition formula as well. One of the things you need to do is use vector addition or subtraction with right-angled or equilateral triangles to calculate the magnitude and direction of the electric field at any point. So that's very similar to doing what we just did with Coulombs law. But instead of working out the net force, you are working out the net electric field. And once you work out the net electric field, you could then work out what the net force would be on an object If it's positive, it'll be in the direction of the field. If it's negative, it'll be in the opposite direction to the field. I'm not going to go through an example for that. It's very much like that calculation I just did in the previous slide. Okay, so now we're going to look at the shape of some electric field around various charged objects. If you are at all confused with any of this, or this is new to you, you haven't seen it, I'd recommend going and using this PhET simulation, which lets you play around with this sort of scenarios that I'm playing around with now, and just get a bit more concrete example of what it looks like. This is also very similar to the shape of what you might have seen with magnetic fields if you've ever done experiments with magnets and iron filings. You can see the magnetic shapes of magnetic fields probably much better than you can see electric fields. There is some practice you can do to look at the shape of electric fields, but they don't always give the best results. So anyway, let's look at the shape. So if we've got a negative charge, remember the direction of the electric field will be the same as experienced by a positive, so opposite charges attract. So the arrow, if you like, will go towards the negative. So it'll be pointing downwards, and we would get an electric field that looks like this. So the lines go towards the negative or away from the positive if you've got it the other way around. And they always should meet the charged object here at 90 degrees or at a 90 degrees to the tangent. So that's what the electric field would look like around a single negative charge. If we had a positive charge, well then a test charge placed that near that would be repelled. So the shape would look similar, but the field lines would all point away from, because a positive test charge would be repelled. So it would be pushed away from that. Now, if we had a positive and a negative charge, we can almost think about that. Let me grab a different colour just to sort of highlight this. If we're at some point here, well, the negative charge, oh, sorry, I did that the wrong way. The negative charge, small positive test charge, would be getting pulled towards that one, and it would be getting repelled away from that one. So basically, when you added those together vectorially, you'd get something that looks like that. That would sort of, the directions would cancel out and would reinforce if we did that as a little vector addition. So, or if we're right in the middle here, well, it's going to go directly away from the positive towards the negative. This one here will go like that, and it will be in that direction, and like that, and so always away from the positive towards, oops, that's a wonky line, let's do that a bit better, towards the negative. Out here, that's just going to look like that. Let me make sure I get this right. It's a positive, so they would go away, and negative, so they would come towards. So that would be the electric field around a positive and a negative charge. If we had two negative charges, we're going to get something that looks like, now obviously around here, they're both going to go towards the negatives. It'd be the direction by a small positive test charge. But then here, I'm going to get something that looks like that. So if you can imagine, again, if I do the yellow lines, if you put a small test charge here, it'd get pushed that one by that one, by this charge over here on the right, that way by the one on the left. So you would have that net charge going basically straight up there in the middle. And again, how many lines should I draw here? Oops, I'm going to put the arrow there. That'd be sort of symmetrical on this one. Not doing the greatest job here, but that sort of diagram would be good enough to get the marks. And then for two positive charges, it's basically the same shape as two negative, but the arrows are all going in the opposite direction. So let's draw the lines in first this time. And because it's positive, they're all, whoops, didn't know what happened there. They're all going away. Like that. So that's the electric fields around point charges. Finally, let's just look at a plate. So if we had a positively charged plate here, what would happen is we'd get this uniform field around that. We won't worry about the edges for this one. We'll look at that in the next one. And because it's positive, a positive test charge would be being repelled from that. So all those arrows would go away like that. And then if we had a positively charged plate here, so this is between the near and edges of two finitely opposite charged parallel plates. So this is actually the one I'm doing here. And then we had a negative charged plate here. Those field lines would go in this area. We'd get this uniform electric field. So the lines would be evenly spaced. That's how we show it's uniform. And they would go downwards, so away from the positive towards the negative. But then basically at the edges, we would get this sort of bulging effect at the edges as they met the conducting surface at 90 degrees to the tangent. So that's what the electric field would look like between two what we call finite length positively plates. If you're uniform in the middle, we'd get that sort of bulging and distortion at the end. So that is the shapes of the electric fields that you need to know between point charges and plates. And there's one more example that we need to look at in the next slide. Sorry, I'll tell a lie, there's two more little situations we need to know about. The first is what happens inside a hollow conductor. Now, if we've got this hollow conductor here, you can probably already picture on the outside, we would get that field that looks like what we just looked at previously. And because it's positive, they would be all repelled, pushed away, so the arrows would be going around like that. However, inside that circle, basically there would be no electric field. And if you think about it there, if you put a charge there, it's basically going to be getting a positive charge is going to get repelled in all directions. So it's going to have some force going there, some force going up. Basically, all of those things are going to cancel out. And even if you come over here by the edge, it's going to be getting pushed more, I guess, from this closer side because there's more positive charge, but there's a greater radius or a greater distance of charge around that side. So basically, you know, the ones on this side might be longer, but then there'll be lots of short ones on this side, if you like, that would add up vectorially to cancel out. So basically, inside a hollow conductor, there is no electrostatic charge. The next one we need to know about is they call them irregular shapes, and we talk about corona discharge. We often talk about this and talk about a pear-shaped conductor. So this is it's got a point at one end and it's broad at the other. I may do a demonstration in the lab with these. But basically, where you have a sharp object, you get the accumulation of charge. So charge will build up near this sharp object. So there'll be a concentrated charge just because of the charge all repelling itself within the object. And what that leads to is the fact that you get a very strong electric field. And we show that by having lots of lines really close to each other near the sharp point. And then as we move away from that sharp point, we then have less, or the electric field is not as strong. So we have less lines, if you like, in our electric field. So that's sort of what the electric field would look like around a pear-shaped conductor. Now, because of that shape, what happens, let me find a highlighter pen here. What happens is you get a really strong electric field in this sort of area here. You can get such a strong electric field that basically it is able to rip electrons out of the air molecules. So the nitrogen and oxygen molecules in air, the electric field there is that long, so it can basically rip the electrons out, they become ionized. That is what leads to either that spark, that lightning spark, because as it becomes ions, electricity can flow through charged particles, and an ion is charged, and normally a gas molecule is neutral. That leads to that spark, and it allows like electricity to be conducted in things like lightning, but also, and hopefully I'll get a chance to, or if you haven't already seen, demonstrate a corona discharge and what that looks like and sounds like one day, either in the lab or I could probably do it on a video lesson as well. So that is the corona discharge due to the strong electric field near sharp points. So that completes our story of electric fields. Hopefully it's a fairly straightforward topic that you can get through fairly quickly, so that we can quickly get on to, in the next week, looking at the movement of charged particles in electric fields, which is probably, I guess, a slightly more interesting application of the stuff that we've been looking at. Cheers.